The determination of spectroscopic terms is a very important concept of atomic physics. Particularly, this concept is needed in dealing with the atomic spectra. And in this regard, we have to discuss two types of problems. First of all, we have seen in the earlier lectures how to determine the spectroscopic term in case of the atoms having only one optical electron. When you say optical electron, that means the electron which determines the total spectroscopic properties of the atom. So when there is only one optical electron, the writing spectroscopic term is very easy, and you have learnt it in the previous lectures. But now our aim is to deal with the problems to write the spectroscopic terms for the atoms with several optically active electrons. And actually this problem needs two concepts, two types of coupling. That is the coupling of two angular momenta, that is the orbital angular momentum L and the spin angular momentum S. Actually, when these two angular momenta are added together, we get the total angular momentum of the atom. So in this chapter, first of all, we will see the concept of LS and JJ coupling, and then we will learn how to write the notation for the different spectroscopic terms. One thing here we should note that this chapter is very important for the competitive examinations. When you will see the question papers of different Public Service Commission examinations for physics optional, always questions from this spectroscopic notation is asked. Although it is also important for the university examinations, so you can say that these lectures on the LS and JJ coupling will be very important or equally important for the students of or for the students preparing for university examinations and also for the competitive examinations, particularly the NET JRF examination or the different civil services examinations of different states, and also the Union Public Service Commission. This is very important. So in this regard, we are first of all going to discuss LS coupling. Actually, the concept of LS coupling will be dealt in not only in one lecture, it will need more than one lecture. So this is actually the first part of the lecture on the LS coupling. In fact, this LS coupling is also known as Russell-Saunders coupling. In fact, these Russell and Saunders were actually two astronomers who first of all studied the atomic spectra emitted by stars, and while studying the atomic spectra of emitted stars, they used the concept of this LS coupling. Okay, so that's why we also call this LS coupling as Russell-Saunders coupling. Okay, in fact, this LS coupling is found particularly in lighter atoms. Okay, and if you want to deal with the LS coupling in atoms or particularly lighter atoms, then there will be actually three perturbations, and in a particular order we will deal with the problem taking these three perturbations under account. These three perturbations are first one is a spin correlation. Then we will consider the residual electrostatic interaction, and finally we will consider the spin orbit interaction. Okay, when you say a spin correlation, that means the spin angular momenta of the different atoms, different electrons, not atoms, but spin angular momenta of different electrons or different optical electrons of the same atom will get added. Okay, and then we will get actually the total spin angular momentum of the atom. And in electrostatic interaction, there will be the coupling of the different angular momentum of the optical electrons, and that will result actually into the total angular momentum L. And when you talk about the spin in orbit interaction, that means there will be a coupling of the total angular momentum or total orbital angular momentum and the spin angular momentum. That is, there will be a combination of L and S. Okay, this was in brief what we will do in these perturbations. Now, one by one in this particular order, we will see how this LS coupling is resulted. So first of all, we consider the first perturbation, a spin-spin correlation. Okay, as I have told you that when there will be a spin-spin correlation effect, then the spin angular momentum vectors of the optical electrons are strongly coupled to one another, and after that coupling we get actually the total angular momentum, total spin angular momentum of the atom. So if you consider that S is the resultant spin angular momentum vector, and this S1, which I am writing by a small letter, S1, S2, so on, these are actually the spin angular momentum of the individual electrons of an individual optical electrons of an atom. Then the resultant spin angular momentum of the atom will be simply the vector sum of the individual spin angular momenta. Okay, actually this resultant spin angular momentum vector S has a quantized magnitude. Its magnitude is quantized and it is given as mod of S is equal to S times S plus 1 into H bar, square root of S into S plus 1 times H bar. Here actually this capital S is the resultant spin angular momentum quantum number. Capital S, this is actually the resultant spin angular momentum quantum number. Okay, so it is quantized because capital S will be a number. Now we will see what will be actually the value of this S. First of all, see the value of S will lie between its minimum and maximum value. Okay, and minimum value, when you will find the minimum value of S, then after adding the number 1 step by step, you will get the other values. And the maximum value of this spin angular momentum quantum number capital S is simply equal to S1 plus S2 plus S3 and so on. Okay, when you say minimum value, then you have to take the minimum value of the vector sum of these individual spin angular momentum vectors. Okay, then the second value will be simply the minimum value plus 1, the third value will be minimum plus 2. Okay, in this way the last value, that the upper limit of the value of S will be simply the scalar sum of all these magnitude of the spin angular momentum of the individual optical electron. Okay. Now, when you have the maximum value of this spin angular momentum vector, then actually that in that state the atom has the lowest energy. It means maximum value of S represents the lowest energy of the atom. Why in this case the energy is lowest, you can easily understand. When S is equal to S max, then you can see this S max is simply equal to S1 plus S2 plus S3. And if the resultant of vectors is simply equal to the magnitude of the sum of the sum of the magnitude of the vectors, this takes place only when all these vectors are parallel to one another. So in this condition, you can say that S1 is parallel to S2, this is parallel to S3, and so on. And if all the spins are parallel, then actually the energy is at its lowest value. Okay. Now, if this spin interaction does not take place, it means there is no perturbation. In fact, in that condition, you have an energy level. Let us say this is the energy level when there is no spin interaction. Okay. So this is called actually the unperturbed energy level. This is called unperturbed, that is undisturbed or unperturbed energy level. Okay. And when this spin interaction takes place, then actually this energy level is splitted into 2s plus 1 different energy levels. Okay, 2s plus 1 different energy levels. So, and what will be that 2s plus 1? That actually this 2s plus 1 is equal to the values of this s. It means if s has, let us say, 2 values, this unperturbed energy level will be splitted into 2 levels. Okay. And if this s has, let us say, 4 values, then this unperturbed energy level will be splitted into 4 levels. Okay. Now let us find the value of the total spin quantum number s by taking some example. Let us consider there is only one optical electron. So if there is only one optical electron, there will be no spin interaction, because interaction will take place only when at least there are 2 electrons. Then the spin of the 2 electrons will get interacted. But here I am considering that there is only one electron, so there will be no spin interaction. So if there is one electron, then s will be equal to half. You know the spin quantum number small s is equal to half. So in this condition, this capital S, that is the resultant spin quantum number, and the individual spin quantum number, both will be same, and that will be equal to 1 by 2. So here there is actually no spin interaction. Okay. Now we will see how many levels will be in this case. Since s is equal to 1 by 2, so you know the multiplicity of this state will be 2s plus 1, that is 2 into half plus 1, that is 2. And so this is actually called the doublet level. Okay. Now let us consider there are 2 optical electrons, and if there are 2 optical electrons, then the individual spin quantum number will be what? This is s1 equal to half and s2 equal to half. Okay. Now what will be the total spin angular momentum quantum number capital S in this case. As I have told you, S has actually 2s plus 1 values lying from minimum S to maximum S. Since there are two spin quantum numbers, so the minimum value S minimum will be what? S minimum will be simply difference of S1 and S2, and this will be actually 0 because both are equal to 1. And S max, what will be the maximum value? This is simply S1 plus S2, and that will be 1 because 1 by 2 plus 1 by 2 is 1. So you have to write all values in this manner. First of all, write the minimum value, then add 1 in the minimum value. This will be equal to 1. And you can see this is the minimum value and this is the maximum value. So there will be only two values of S, and those are 0 and 1. But in general form, when you write the formula, then you write S equal to mod of S1 minus S2. Again, because S1 minus S2 is the minimum value, and then S1 minus S2 plus 1 and up to S1 plus S2. And so as I have told you, there is no need to write the values of S in this manner. You can easily find this in this manner, that first of all find the minimum value and then the maximum value, and runs from minimum to maximum just adding 1. Okay. So in this condition, S is equal to 0 and 1. When S is 0, then multiplicity will be what? Multiplicity is 2s plus 1, and this will be 2 into 0 plus 1, that is 1. Okay. This multiplicity is for S equal to 0. And when S is equal to 1, then multiplicity will be 2 into 1 plus 1, that is 3. Okay. When 2s plus 1 is equal to 1, this is called actually singlet level. And if the multiplicity is 3, this is called triplet level. Okay. This is called triplet level. Singlet level means it will be not splitted, but triplet level means it will be splitted in 3 levels. Okay. In this way, you can find the total spin angular momentum quantum number for any number of optical electrons. And here you should remember just a trick how we can write the values of the different values of the total spin quantum number when the number of optical electrons is given. In fact, the number of optical electrons will be either even number or odd number. Okay. If the number of electrons is even, let us say n is the number of electron and n is even. When n is even, then definitely S will have these following values. S will be 0, 1, 2, so on and up to n by 2. For example, if you consider that n is equal to 4, it means there are 4 optical electrons. Okay. And a spin correlation effect takes place. Then what will be the total spin quantum number S? Or you can also say that what will be the total spin angular momentum S. Okay. This will be equal to what? This will be equal to 0, 1, 2, 0, 1, 2, because the last number should be n by 2. So first number is 0, last number is n by 2, and here n is 4. So this will be 4 by 2, and that is equal to 2. So in this condition, S will have 3 values, 0, 1, 2. Okay. And if the total number of electrons n is odd number, like this is 1 or 3 or 5 or 7 and so on. In that condition, S has these values. These are half integral values: 1 by 2, 3 by 2, 5 by 2, and up to n by 2. Okay. For example, if you consider that n is equal to 1, then S will be equal to what? First value will be 1 by 2, and since it is 1, so the S will have only one value, and this is equal to 1 by 2. As you can see, I have already found this value here. For one electron, S is equal to 1 by 2. Okay. And if S is equal to let us say 2, n is equal to 2, this is an even number, then you can see what will be the values. Values will lie between 0 and 2 by 2, that is 1. So there will be only two values, 0 and 1. And you can see here in this example we have considered 2 electrons, and for 2 electrons S is equal to 0 and 1. And if you consider that n is equal to 3, this is an odd number. In that condition, the values will be what? The first value will be 1 by 2, and last value will be 3 by 2, n by 2, that is 3 by 2. So this first two values will be the values of S. Okay. And if it is, let us say n is equal to, let us say 9, then what will be the value of S? This will be 1 by 2, 3 by 2, 5 by 2, 7 by 2, and 9 by 2. These are the values of S. Okay. So I think you have understand. In general, if there are n electrons, then what will be the values of S? Okay. One thing here is very remarkable, that in case of even number of optical electrons, S has integral values. You can see S equal to 0, 1, 2, 3, so on up to n by 2. These are integers. Okay. And if n is an odd number, that is the total number of electrons is odd, then S has half integral values. So you should note that the total spin quantum number capital S may have integral values, and it may have half integral values. Okay. Both type of values are possible for this S. Okay. Now we will consider the second perturbation to determine the LS coupling. The second perturbation is called residual electrostatic interaction. Actually, when there is a residual electrostatic interaction, then the individual orbital angular momentum vectors, which we denote by the symbol L, that gets added together. Okay. They are actually added together very strongly, and due to the combination of these L vectors, we get the resultant orbital angular momentum vector capital L. Okay. It means you can say that this capital L is equal to L1 plus L2 plus L3 plus so on. Actually here L1, small l1, small l2, small l3, these are the orbital angular momentum vectors of the individual optical electrons of an atom. And when they are added together vectorially, then we get the resultant angular momentum of the atom. Okay, and that is denoted by the symbol capital L. Actually, magnitude of this capital L is also quantized, and its magnitude is given by this. Mod of L is equal to L into L plus 1's square root times h bar. Okay, and this L is actually a constant of motion. Here, this capital L is the resultant orbital angular momentum quantum number. Capital L is what? This is a resultant orbital angular momentum quantum number. Okay, and what are actually the values of this capital L? That is the resultant orbital quantum numbers values again lies between a minimum value of these vector sum and its maximum value. You know, maximum value is simply equal to the sum of the magnitudes, and minimum value, in case of minimum value, we have to actually obtain the minimum value by vector addition. So L's values will be what? This will be L1 plus L2 plus so on minimum plus L1 plus L2 plus so on minimum plus 1, and you have to take modulus because this minimum may be L1 minus L2, this may be L2 minus L1. It means it will be negative, but when you will take the mod, then the value will be only positive. Okay. Now, just for example, if you consider that there is only 2 electrons, then L minimum will be what? If there is 2 electrons, then L minimum is equal to L1 difference L2. Okay, or you may write it mod of L1 minus L2 in case of 2 electrons. And if you want to find the maximum value of L in this condition, that L max will be simply equal to L1 plus L2. And then all values from L minimum to L maximum are obtained simply adding 1 in the smaller value. Okay. Now this different value of L actually represents the different energy state of our atom. And just like S, when this capital L is largest, then the energy corresponding to that state is lowest. So largest L refers lowest energy state, remember. Okay, and the lowest L will refer the largest energy state. Okay. Now, when this interaction actually takes place, the energy levels which was unperturbed, which was an energy level in unperturbed state, that is when there is no this LL coupling. In that condition, the different energy level is denoted by the later symbol. In fact, if L is equal to 0, that represents S level. If L is equal to 1, that level is called P level. L equal to 2, this is D level. L equal to 3, F level. L equal to 4, G level, and so on. Okay. Now, to clarify this concept, how we will find the total orbital angular momentum quantum number capital L, let us take some specific example. We are going to see how we can calculate this capital L. In first example, I have taken here 2 electrons. One electron is 3p electron and another is 3d electron. Okay. As you can see, if you are considering an optical electron which is in fact in p subshell, of the third shell, that is 3p electron. And for p electron, the orbital quantum number small l1 will be equal to 1, because for s electron, orbital quantum number L is equal to 0. For p electron, orbital quantum number is 1. For d electron, orbital quantum number is 2. And for f electron, it is 3. Okay. And this, for 3p electron, L will be equal to 1. And I have denoted it by L1. And for 3d electron, for d electron L is 2, so L2 is equal to 2. Although I have obtained here L by the actual process, but by a trick you can easily find it. First of all, to get the value of capital L, first of all find the minimum value of L. So L minimum will be what? You can find the L minimum by mod of L1 minus L2, or you can take L1 difference L2. Okay, and you can see this will be mod of 1 minus 2, or 1 difference 2. 1 minus 2 is minus 1, but when you will take modulus, this will be plus 1. And difference of 1 and 2 is also 1. So the minimum value of L is 1. Now find the maximum value, L max. Maximum value is simply equal to L1 plus L2. So this will be 1 plus 2, that is 3. Now, if to get the all values of L, you should write first of all the minimum value, that is 1. Then write minimum value plus 1, and that will be equal to 2. Then write this value 2 plus 1, that will be 3. And as it is the maximum value, so this will be the last value. So what are the values of L? You can see this will be 1, 2 and 3. 1, 2 and 3. You can see I have obtained it here. These are 1, 2 and 3. Now L equal to 1, you can see this represents the p state or p level. L equal to 2 represents the d state or d level, and L equal to 3 represents the f level. So these represents actually the p, d and f states. Okay. Now we consider an example where there is actually more than 2 electrons. For example, let us take 2p electron, 3p electron and 4d electron. Let us consider. In fact, when there is more than 2 electrons, then we follow a particular technique to find the total orbital angular momentum quantum number capital L. In this condition, first of all, consider any 2 electrons. Although the optical electron is more than 2, you have to consider first of all 2 electrons. And for those 2 electrons, first of all find the value of capital L. Then that capital L will be combined to the third electron. Okay. So let us see. So first of all we consider the 2p and 3p electrons. Okay. Now for 2p electron is in p subshell, so L will be equal to 1. And for 3p electrons, this L is again 1. Okay. So what will be the minimum value of L in this condition? You can see minimum value will be 1 difference 1, that is 0. And what will be the maximum value of L? Maximum value will be 1 plus 1, that is 2. Okay. So now write the all values. First of all, you have to write the minimum value, then minimum plus 1, that is 1. Again 1 plus 1, that is 2. This is the maximum value. So the values of L in this condition will be 0, 1 and 2. 0, 1 and 2. This 0 represents actually S state, 1 represents P state, and 2 represents D state. Okay, so you can see, if you consider that this L is equal to L prime. Why I am considering L prime? Because finally we will have to obtain L, because one electron is remaining here. Okay, so L prime is equal to 0, 1 and 2, and these represents actually the SPD states. Now consider there is an electron for which the orbital quantum number is L prime and its values are 0, 1 and 2. Let us consider. And the remaining electron is 4d electron. Okay, and for 4d electron L is equal to, let us say, L3, and this will be equal to 2 because the electron is of d subshell. So now you have to find the resultant L by the combination of these angular momenta. Okay, since L dash has 3 values, so one by one we will combine the values of this L dash with the value of L3. So first of all, consider L dash equal to 0 and L3 equal to 2. See here, L dash equal to 0 and L3 equal to 2. Okay, so in this condition, when L dash is equal to 0 and L3 equal to 2, what will be the minimum value of L? L minimum will be what? This will be 2 minus 0, that is 2. And what will be the maximum value? Maximum value will be 2 plus 0, that is 2. It means in this condition L has only one value, and that value is equal to 2, and that represents the D state. Okay, now we will consider the next value of L dash, that is 1. So L dash is now 1 and L3 is equal to 2, and you have to combine these two. So again find the minimum value of L. L minimum will be what? This will be 2 minus 1, that is 1. And what will be the maximum value of L? This will be 1 plus 2, that is 3. So you have to run from 1 to 3 at a step of 1. So what will be the values? First value will be 1, another will be 2, and then there will be 3. So 1, 2, 3 are the values of the resultant angular momentum L. 1, 2, 3. And these represent PDF state. Now finally we will consider the third value of L dash, which is actually 2, and L3 equal to 2 and 2. Okay, so see here, L dash equal to 2 and L3 equal to 2. In the similar manner, you can find the minimum value. Minimum value will be 2 minus 2, that is 0. See here, maximum value 2 plus 2, that is 4. See here. So you have to move from 0 to 4 at a step of 1. So what will be the number? Number will be 0, 1, 2, 3 and 4. Okay, and these are actually the states SP, D, F and G. So in this condition, you can see after combining the angular momenta of these 3 electrons, 2p, 3p and 4d electrons, what are the states? You can see first of all we get sp d state, then we get d state. It means there will be 2d. Here there is again pdf state, so there are 3d. Okay, 3d. And again you can see here is d, so there are 4 d's. Okay, 4 d's. Sorry, actually this is not, this is the combination of only 2. Here we get the values for the resultant angular momentum capital L after adding the angular momenta of the 3 electrons. So count here d state, and again lastly here the d state. So there are 3 d's in this case. And similarly you can see there will be 1s, 2p and 2f and 1g states. So you can say that in all we obtain 1s, 2p, 3d, 2f and 1g states. Okay. So in this way you can find the total angular momentum L of an atom by adding the individual angular momenta of the optical electrons. In case of 2 electrons it is very easy. In case of more than 2 electrons you have to first of all group the 2 electrons, find then capital L, then that capital L will be added to the angular momenta of the 3rd electron in the similar manner. If there will be 4, then there will be actually the 3 steps. First of all 2 electron will be added together, again 2 electron, and then we will add those 2 angular momenta. Okay. Lastly we consider the 3rd perturbation, which is called a spin-orbit interaction. Actually this is a spin-orbit magnetic interaction. Okay. So in fact in this case, due to this interaction there will be a combination of the orbital angular momentum vector L and the spin angular momentum vector S, and due to this combination we get the total angular momentum vector J, which is given by the vector sum of L and S. It means first of all you have to add together the orbital angular momenta small l, then you get capital L, and after coupling of the small s we get the capital S, and then these L and S are coupled together, and this gives the total angular momentum J. Okay, this gives the total angular momentum J. This total angular momentum J is also quantized, its magnitude is also quantized, and it is given by mod of J equal to J into J plus 1 into H bar. J is actually called the total quantum number. It is called total quantum number, and this J will have actually J minimum. This will be actually equal to difference of L and S, and J max will be equal to what? This will be L plus S. Okay, and all values of J will be from J minimum to J maximum getting by adding successively 1. It means the difference of the 2 successive values of J will be equal to 1. Okay, so all together there will be 2J plus 1 values. Okay, and you can see that I have written here the value of J will be mod of L minus S. This is actually the minimum value, and mod of L minus S plus 1, this is next value, and the last value will be L plus S. Okay. Now as you have seen that L has only integral value. L has only integral values, only integral. But this S, this may have integral value. When the total number of electron is even, then S is integral, and it also may be half integral. Half integral. So you can see that the total quantum number J may have integral value and half integral value, because L is always integral. But when S has also integral value, then L plus S or L minus S will be also integral. So J is integral if S is integral, and J is half integral if S is half integral. It is common. Okay. Now this J has 2S plus 1 values if L is greater than S. Mark this. If L is greater than S, then J has 2S plus 1 values. But if S is greater than L, then J has 2L plus 1 values. So you can say that J has either 2S plus 1 values or 2L plus 1 values. That depends on the fact that L is greater than S or S is greater than L. In case when L is greater than S, then J has total value 2S plus 1, and when S is greater than L, then J has total values 2L plus 1. Okay. Now, any unperturbed energy level is splitted either into 2S plus 1 energy levels or 12 plus 1 energy levels, depending on the values of L and S. When L will be greater than S, then the energy level will be splitted into 2S plus 1 level. And when S is greater than L, then an unperturbed energy level will be splitted into 12 plus 1 energy levels due to this spin orbit interaction. Okay, and each level will be characterized by a particular value of J. So different value of J actually represent the different energy levels. So this was actually a basic idea of the LS coupling. How LS coupling takes place. If you want to deal with the problem for optical electron system, then the what will be the process? I am just giving a brief account of it. First of all, you have to find the total spin angular momentum by taking the resultant of S1, S2 and so on for the individual optical electron. Then find the total orbital angular momentum, and this is the vector sum of L1, L2 and so on, where L1, L2 are the angular momentum of the individual optical electron. Okay, and once you get the resultant S and L, then combine this L and S. There is a combination of L and S, and this combination actually gives J, which is called total angular momentum. Okay. In fact, when this LS coupling takes place, in that condition, the group of the different J levels forms a fine structure multiplate, and the relative spacing of the fine structure levels within a multiplate is governed by a particular rule, and that rule is called length interval rule. And this length interval rule is a very important fact to decide the energy levels. So in the forthcoming lecture on this LS coupling, we will discuss two facts. First one will be length interval rule, and the another will be the concept of normal and inverted multiplates. And this is very important for the civil services examinations.